Hello everyone, I am Ashley Lozano and I'm joined by Mohammed Al Hashim and Faisal Alganaz, and we formulate the team for project 21080, which is a high throughput, environmentally friendly hydrodesulfurization unit. And as of course, we are all a chemical engineering major. All right, as mentioned before, this is project 21080, and our mentor is Mr. Fred Brinker, and this is our poster board. And if you'd like to go ahead and pause it to analyze this a little further, we will go ahead and cover all of these further into depth throughout the presentation. And then we will also cover the introduction, the problem description, methods of design, major pieces of equipment, and our final result. To start off, hydrodesulfurization units, or HDS systems, are systems used in oil refineries to reduce the sulfur content in specific oils, more specifically those that are combustible, such as gasoline and diesel. And the removal of sulfur compounds and contents ensures that the products follow EPA standards, which means that they decrease the emissions and that are harmful to the environment, for example, sulfur dioxide. And it also decreases engine corrosion. It increases the effectiveness of catalysts and the cost and effectiveness of oil refinery processes. For a product description, this project includes an oil blend feed that is vaporized and mixed with hydrogen to introduce into a packed bed reactor, or PBR, where the sulfur compounds are able to react with hydrogen for further removal from the oil blend. This further goes into a series of heat exchangers to ensure the recycling of heat energy and reduce the energy costs. And the mixture gas gets introduced into a cold high pressure separator where it's separated, and then a distillation column where we are able to gather up our final oil blend, which has little to no sulfur content in it. And then from this distillation column, we are also able to get some sort of sour gas, which is mostly hydrogen, of course, which then goes into an amine contactor, where it is separated and created into sweet gas, where, of course, it's also mostly hydrogen. And then this is reintroduced into a system as our hydrogen recycle stream. To methods and pieces of equipment. For methods, we went ahead and had several methods of design that we followed to ensure that the system works properly and efficiently. So one of the most important sections would, of course, be our catalytic reaction that is undertaking in the packed bed reactor. And this is where the oil and hydrogen are mixed and are reacted with the aid of a catalyst, where compounds such as benzothiophene, dibenzothiophene, and carbazole are degraded into other products that are more easily removed from the oil blend further down the line. Another one would be heat integration, which is another term is the recycling of heat in the system. Through the use of multiple heat exchangers, the required fire heater's duty is kept to a minimum and utility costs are lowered. And then, of course, we have the hydrogen recycling stream, which is also used to reduce the operating costs. This process reuses an unreacted hydrogen from the post-reactor process and introduces it back with newly added hydrogen to meet the reactor's startup cycle conditions. Now we'll go ahead and pass it over to Mohammed Al Hashim. Thank you.
So our first major piece of equipment is our packed bed reactor with 2 catalyst beds. It has the following operating conditions of 290 Celsius and 77 bars. It has a total volume of 177 meters cubed, and the catalyst that we are going to use is nickel molybdenum alumina with a total active volume of 104.6 meters cubed and an aging rate of 1.75 degrees Celsius per month. The next piece of equipment is the cold high pressure separator. It has a length of around 11 meters, a diameter of around 3.7, and a total volume of 120 meters cubed. The capital cost of this piece of equipment was found to be $1.8 million with an operating cost of around $183,000 per year. The light phase from the CHPS enters in the 15th stage of our 30-stage distillation column. The bottom stream of our distillation column shows that there is a 95% separation rate with almost no traces of sulfur in our diesel. The distillation column is 16.5 meters high and has a diameter of around 3 meters. The temperature profile on the right shows that our distillation column is operating properly. It shows that there is a steady increase in temperature as we go down the column. And the temperature spike right after stage 15 in the middle of the graph is a result of the feed being introduced. It has an estimated capital cost of $6.6 million and an estimated operational cost of $650,000 per year. Next is the Amine contactor. The Amine contactor inlet is the sour gas from the CHPS and the stream of lean DGA. The outlet streams are the sweetened gas that is recycled back into the process and the spent amine, which is sent out. This amine contactor has 10 stages and it is 6 meters tall and 2 meters in diameter. It has a capital cost of $2.3 million and a yearly operating cost of $35.5 thousand. The final piece of equipment is are the hydrogen compressors. There's a total of 6 compressors and they are divided into 2 groups, and each compressor costs approximately $1.73 million. The first group is donated by C101 and they have an estimated operating cost of $52 per hour each. And the second group, donated by C102, has an operating cost of approximately $41 per hour each. I will now hand it over to Faisal and he will be talking about the results and the process flow diagram as a whole.
Thank you, Mohammed. Hello, everyone. My name is Faisal Alganas. I'll be discussing the results and going briefly over the process flow diagram. So stream 59 is our final product stream that includes only biphenyl, diesel, and dibenzopyrrole. Diesel being the most significant, of course, approximately 751.75 kilomoles per hour, which is a 95% separation from the feed. The remaining 5% of the final product stream is naphtha, which is biphenyl and dibenzopyrrole. And we can go ahead and talk about the cost of the process. The capital cost is coming in at approximately $103 million. And that is, of course, adjusted for inflation from the Oil and Gas Journal. And the utilities is $4.3 million per year, which is also adjusted for inflation from the Oil and Gas Journal. Now, if we go over the PFD, I'm just going to quickly process how we go from stream 1 right here to stream 59. So stream 1 enters through a series of pumps, heat exchangers, mixers, and splitters before it enters the packed bed reactor over here. Then the packed bed reactor goes through, the stream that exits the packed bed reactor goes through another series of heat exchangers and a fin fan before it goes into the CHPS. And then the CHPS has 3 outlet streams, one that goes into the distillation column, where the bottoms is going to be our final product, and our final product enters another series of heat exchangers before we have our final product stream. The other 2 outlets is just water, and the one that goes into the amine contactor. And the amine contactor's outlet goes into another series of compressors, knockout drums, and pumps, and the other outlet just leaves the system. These are our references. Thank you very much for watching our video and presentation. Let us know if you have any questions when you see us.